Earlier we have talked about linear constant coefficient difference equations in Chapter 2. And when a system is governed by such an equation, the input xn and output yn satisfy a0 yn, a1 yn minus 1 to an yn minus n. Big N equal to b0 xn plus b1 xn minus 1 all the way to am xn minus m. This is a bit like the continuous time linear constant coefficient differential equation. Now we would like to study such a system from the frequency domain. We take Z transform on both sides and we see that each term on the left hand side, if we apply Z transform, has YZ, this one has YZ, and this one is YZ with an additional delay, and this is YZ with n delays. So we can pull out YZ and we in the bracket we get A0 plus A1Z inverse all the way to ANZ minus n. On the right hand side, we notice that each term has an xz. This is xz with z inverse. So we can pull out xz, and this is the constant, and each term in the bracket has a constant and a delay term. Is a constant multiplied by a delay. The system function hz is the ratio of the two, yz over xz. We can move terms around here to get this ratio here. We move xz to the left hand side and move a to this bracket to the right hand side. This is what we get. And we can see what kind of system. This is a system that we are familiar with, that we have talked about before. What kind of system is this? For both the denominator and for the numerator and the denominator, we can convert them into polynomials in Z. So this is actually a rational system. So we talked about systems that are governed by linear constant coefficient difference equation, and we have talked about rational system, but they are actually the same thing. This is a rational system. Now we can talk about zeros and poles. We can pull out terms, be the constant b0 over a0, and the numerator we can factorize it. Suppose we have zeros as ck, and for the denominator we also factorize it, and we have poles at dk. For such a system, we have talked about the stability before. It is stable if and only if all the poles are inside the unit circle, so all the dk have absolute value less than 1. And for a system that is described by a linear constant coefficient difference equation, we say it has a minimum phase if the zeros are inside the unit circle and the poles are inside the unit circle. We know that the poles should be inside the unit circle for the purpose of stability. But why should the zeros be inside the unit circle too? A minimum phase has both zeros and poles inside the unit circle. Why do we need both zeros and poles inside the unit circle? Before we look at the reason, let's give another definition. Another definition for H that is a system described by LTCCDE. We say HIZ is an inverse of HZ if their product is equal to 1. HIZ and HZ together is equal to 1. That means that HIZ is actually equal to, but is it equal to 1 over H? Now let me ask a question. Suppose we know that both HZ and HIZ, both of them are stable. What does this say about the poles and zeros of H? That means, what does that mean? What's the condition? Well, HI is the inverse of H. So when we take the inverse, the zeros of H will become the poles, whereas the poles will become the zeros. So if both of them are stable, that could mean only one thing. CK, DK should be inside the unit circle, and also the zeros are also inside the unit circle. This K is from 1 to N, and this K is from 1 to M. Almost all the systems that we use are rational system like this one. In this section, we are going to have another look at the frequency response. The question that we ask here is it possible to visualize the behavior of frequency response for rational system, of course, without explicit evaluation? Explicit. Given the system function or given the impulse response, we can always compute the frequency response of H. That is, we can use computer, we can compute the Fourier transform. But now the question that we ask here, is it possible to visualize, to have a rough idea of the frequency response of H without actual calculating the Fourier transform, without explicit evaluation? Let's go back to the factorization form of Hz, like this equation. Let's multiply some z to the numerator and denominator so that the factorization is given in terms of z rather than z inverse. C minus ck, and at the bottom we have k at 1 to n, and then z minus dk. And to compensate, we have extra term z raised to the power n minus m. If we want to calculate the value of h of z for a certain z, then we simply plug in the value of z here and z here, and we take the product after we have each term. Similarly, for the denominator, we compute z minus ck for each k, and then we take the product, we have the denominator. So plugging the z into this expression, we get the value of hz for that z. When we plug in a certain z into the equation, the term z minus ck will be a complex number in general. Let's express this complex number as bk, the absolute value, and a phase term. Similarly, for the denominator, for the term in the denominator, we will express it in polar form, aka ej phi k. Now let's plug in, let's replace z minus ck by bk ej theta k, and the z minus dk by ak ej phi k. Now if we want to look at the magnitude response, which would be z transform evaluated on the unit circle and has with absolute value, then we get b0 over a0 absolute value, and this term here, when z is on the unit circle, this term has absolute value equal to 1. And if we look at this term here, if we take the absolute value here, all the phase term will go away. And we are left with the product of the BK in the numerator and the product of AK at the bottom. How about phase response? To consider phase response, we can simply add up the phase of this term, and this term. So we have the phase of P0 over A0, and then we have the phase of the Z raised to power m minus m. That will be m minus m omega. And then we have the term of theta added together, and then phi added together, that is subtracted. So how are these derivations, the derivations of magnitude like this and phase like this, how are these derivations going to help us in visualize the frequency response? Let's look at one example. Let's consider the 4-point rectangular window. For such a filter, we know the zeros are at -1, j, and minus j. So here's the z-plan. I've drawn the unit circle. It has 1 0 here, 1 0 here, 1 0 here, and the poles here. The poles are at 0, 0, and 0. 3 poles at 0. Suppose we would like to draw the magnitude response as a function of omega. Let's go back to see how those derivation means, what those derivation means. The expression here says that h, except this scalar here, is a ratio, and at the top is the product of pk, and at the bottom is the product of ak. But what are bk and ak? This is where bk and ak come in. bk comes in as the polar in the polar representation of z minus ck. So what bk represent is actually the distance between z and the ck, and z is the point of interest, the point we would like to do the evaluation. And ak, what is ak? Ak is actually the distance between z and the pole. bk is the distance between z and the 0. So at the numerator here we have product of distances, two zeros. And at the bottom, what we have here is product of distances to poles. Now let's return to the rectangular window example. The numerator, we would have the distance to all the zeros. Distance to the 0 at j, the distance to the 0 at minus j, and the distance to the poles. The poles are at 0, so it's z to the 3rd. So now if we want to know the magnitude at the DC frequency, we would then compute the distance to all the zeros. This is the distance, this is the distance, and this is the distance and the distance to the zeros are B1, B2, and B3. And we also compute the distance to the zeros. The distance to the pole. The poles are all at the origin. So this is the distance to the pole. This would be A1, A2, and then A3. They are all the same. But in this particular case, A1, A2, A3 are all equal to 1. So they don't have any effect. Then we will have a value for the magnitude at omega equal to 0. If we take the product of B and divide it by the product of A doesn't have an effect, so just the product of B, and then divide it by 4. This 1/4 factor here. Now suppose the point of interest is we are moving away from the DC frequency towards 2 pi. Suppose this is the point that we want to know the magnitude response. Again, we will compute the distance to all the zeros. Now it's this one, and this one. We take the product and divide it by the distance to the poles. And again, the distance to the pole is equal to 1 in this case, so it doesn't make a difference. We only need to concern ourselves with the product of the zeros. And we can see that as we move, this is B2, this is our B2 now. As we move towards this 0, this distance becomes smaller and smaller and smaller, and when we move to this point of 0, it will become 0. So the magnitude response will gradually decrease to 0. So as we move from 0 to pi/2, the magnitude will decrease to 0. So this is what happened. Gradually decrease to 0. And then as we move towards, and then as you move away from this 0, that's already equal to 0. So as we move away from this 0 at J here, the magnitude will come back up. So the magnitude will come back up again. And as we move towards this 0 again, the value will go to 0 again. So here, the value will go to 0 again at pi. And this is the magnitude response of a rectangular window that we have talked about earlier. We do not need to consider the other half minus pi to 0 because it's symmetric. And using this approach, we can get a rough idea of how the magnitude will behave in the frequency response without actual evaluation of the actual value. Alright, that's section 5.3. We will leave section 5.4 as a reading assignment. So please read up section 5.4 yourself.